So far we've talked about how to do finite difference, but we haven't talked about when would it not work to do finite difference, so that's what we're talking about now. Someone once asked me when I brought this up, is it all about getting trapped in a local minimum that's not global? And that is an important issue in optimization in general, but it's not related to whether we're doing finite differences or some other kind of gradient computation, so that's not the issue. Take a minute to think about what kind of things in an optimization problem could make finite difference not work so well. Pause the video and then come back and we'll talk about them. Okay, welcome back from pause. So anything with sharp corners, like the absolute value function or the maximum of 0 in x, which is known as a rectified linear unit, or ReLU in neural networks, those don't have a derivative right here or right here at the corner. And in some sense you might say, well, I don't worry about that because really what's the chance I'm right at that corner, right? I'm probably out here or over here, so maybe it's not going to be an issue. The problem is the optimum solution is probably right there or something, or right there, so you kind of want to be there. We've seen this happen with lasso, which is a way of doing regression and trying to select which variables are the most important. We were summing the absolute values of the weighting coefficients, or sum of absolute values residuals. Obviously, you've got an absolute value there. There's a really interesting mathematical technique called compressive sensing that's related to lasso, and you have absolute values going on there. So what do we do in situations like that? Well, it turns out there's a sneaky way to reformulate absolute value and maximum value using two more decision variables. You might say this decision variable is now the difference of a positive version of itself and a negative version of itself, but this one has to be positive. So if we had a 0 and a -3, then the decision variable, a 0 and a 3, then the decision variable would be -3. And then you can add these two in the objective function and you're adding the absolute value. So that was a key insight that made compressive sensing work pretty well. You could just run a nonlinear solver and hope that it works, but be skeptical and do your best to check that you got a reasonable solution. There are methods that methods for nonlinear programming that don't use gradients at all. So evolutionary method is one of those, simulated annealing. Nelder-Mead simplex is another one. You might see it's different than simplex LP. Simplex LP is for linear problems. So those are some things you can do. Another thing that might happen is step functions. So anything where the objective function doesn't change when you change the decision variables just a tiny bit. So anything like floor, ceiling, or round can do that. Anything with an if statement or rank statements or VLOOKUPs, so those can all cause it. Here's an interesting way it can happen. If I wanted to predict the probability that someone, let's say, gets cancer based on how much they got exposed to a chemical, I might have the blue data here and I'm doing logistic regression, which is great. You might say, instead of doing all this complicated log likelihood stuff, why don't I just say any prediction that's over something like 0.6, I'm going to say, okay, I'm going to say that's predicting cancer. And anything that's under 0.6 is predicting not cancer. So here we're just saying, if my prediction is bigger than that, then predict a 1, otherwise a 0. And then I could ask, did I get a true positive or false positive or true negative, false negative? So just say, if the person didn't get cancer and my prediction was not cancer, then would that be a true positive or false or true negative? I'd have to think about that. And then I can count all the true negatives and true positives and stuff. Oh, try that again. Just by summing my binaries. And then I could say, let's minimize the sum of false positives and false negatives. Seems reasonable. You might want to apply a weighting coefficient. Maybe false positives are worse than false negatives, for example. The problem here is, what if I change my my shift parameter a little bit? Let's say it's 50.001, which is what we would do when computing finite differences. All my predictions will change just a little bit, but none of them went above or below this 0.6 where they hadn't been below before. So my objective function did not change when I changed my decision variable. Solver will say, oh, I changed that a little bit. I got 0 difference in the y value. I must be at a flat spot. I'm done. I'm stopping. So that kind of if-then thing can cause real trouble for nonlinear programming. It's better to use something like log likelihood or cross entropy, which does change a little bit. Look at this when I change that. Did you see a digit changed? So that gives solver a little hint of what's better and what's worse when you change the decision variables. So what to do for those? Reformulate to use smoother functions like cross entropy. Maybe use a larger delta x, so hopefully you'd be hopping from one flat spot to another, but delta x is not adjustable in solver. Even if solver knows the decision variable must be integer, you would think it would then use a delta x of 1 to go to the next integer, but nope, and there's apparently no way to adjust it. Or again, run one of these methods that don't use gradient calculations at all. Another place this can happen is at the boundary of the feasible region. If you're right here and you try to use a delta x and get over here, I highlighted some, I have an open circle here, but really you'd get an answer that's not at any particular y value. It would just be not a number or divide by 0 or log of a negative or something. So that can happen with nonlinear programs that we do called barrier methods, where we say, to keep myself from crossing this constraint, I'm going to start applying a kind of a penalty to my objective function. Say that really hurts the closer I get to that constraint. Sometimes those barrier functions are undefined on the other side of that constraint. So what can you do about this? If you're using like a logarithmic barrier function, you can probably take symbolic derivatives, but you can't help solver with that. It won't accept help with symbolic derivatives. You could say, if you're programming it yourself, try forward difference, and if that doesn't work, then try backward difference. But again, solver can't be programmed differently to do that. And one thing with solver is the instant something goes wrong, like not a number, it just stops. It doesn't say, oh, you know what, I violated a constraint, never mind, let me go try something else. So that's something you have to watch out for. Another thing that can happen is the objective function could have randomness. So see, if you were trying to estimate the slope over on this side to get toward that minimum, depending on which pair of points you picked, you might get a positive slope or a negative slope. Our objective functions have randomness in the evaluation when we're doing something called Monte Carlo methods. Monte Carlo is a city famous for having casinos, and there are math methods of evaluating functions where we throw random numbers in and kind of average what we get out. There's also something called discrete event simulation. Here's a picture of an example. Let's see if I can find it here. So if you want to say what's the average waiting time in an emergency department based on how many doctors and nurses and patient stretcher movers that I have on hand, you can build a simulation that says people arrived at these exact times and took this long to get served by the triage nurse, etc. And you can track how many patients are in the clinic. But all those patient arrival times and patient service times are random, and if you ran the simulation again, you'd get slightly different numbers. So we talk about that kind of thing in math419, 519 sometimes. What can you do? There's a technique from statistics called response surface methodology, which says instead of just a few points here, let me pick more than that and then try to fit a parabola to it maybe. That's also called meta models in stochastic simulation optimization. Maybe use a larger delta x. If you use a delta x large enough, maybe this point is guaranteed to be lower than that point, so you get an accurate estimate of the slope. Maybe sample data more than once at each point, so you would decrease the amount of randomness in the averages there. And then the last thing that leads into our next module, sometimes the evaluation of the objective function just takes too long. So if you have an engineering fluid flow partial differential equation problem, let me show a quote from a person on the internet here. This person says, in mechanical engineering, aircraft design, we can ignore this part, but this person says, a single evaluation of the objective function could take 1 to 2 weeks. So at that point, you really have to decide how much time you can put into optimization stuff. So that's one issue. Another issue is in big data, doing regression, you'd have to compute all the residuals and add them up, or square them and then add them up. And that can take a long time, especially if you're doing neural nets where each predictions the neural net gives you takes more time than just simply computing residuals. So what can we do in those cases? Well, if the objective function is a sum or product of terms, one for each data point, you can use something called stochastic gradient descent, which we're going to talk about in our next module. Or maybe you could use response surface methodology in that engineering kind of situation.